comment a little bit about what it means to understand the mathematics. First place, we're going to test our period versus length, T versus L, to see if we get a power function. If so, we want to find out what our y factor is. Having found out our y factor, we can find the power of p, log of the y factor over log of 2. That gives us a power of p, so our model is y equals a x to the p, some multiple of x to the p. Well, once we know p, we can scale our graph by just putting one point on it, and that gives us a value of a. Now, we might find that the graph goes really well through our data points, so that we might find a if each of our data points is correct, and see if we get the same value of a every time. We wouldn't get the same value of a every time, but we might get values that are very close. If not, then we want to use the curve that we think best fits the trend and take a point on the curve, not a data point, which is what I always advocate. You never try to use a data point. If you do, you're kind of stuck using all your data points to see if you get the same value of your constant a. That's tedious if you have more than 3 data points. If you got 20 or 30 data points, you don't want to do that. You want to go to a nice trend curve. Excuse me. Okay, so that's all a process that we understand pretty well. Maybe a little shaky on this value of a, but finding the y factor, testing for a power function, finding the y factor, that's pretty secure. There's a simple relationship that allows us to get p, and you should know that relationship, but not everybody understands the logs well enough to really lock that in, so you just kind of look that up if you need to. Although if you've had pre-calculus, it ought to be locked in. Okay. And so forth. Now, in parentheses, there are a couple more things that we would ordinarily do. We would use at least squares curve fit to see what the power is, rather than testing data points or testing one point and scaling the graph. But that's equivalent to scaling the graph with a little more attitude and a little more accuracy. So first I say, let's learn to scale the graph. There are many reasons that we want to be able to do that. But ultimately, when we analyze this data, we would use some sort of a least squares curve fit. It's not a linear least squares curve fit. It's a curve fit to a power function. And that actually gets pretty mathematically complicated. Of course, you can always use software to do it without understanding how it's done at all. But we're trying to emphasize understanding here, and using software to do it without understanding what the software does isn't the best way to gain understanding. So I stick with the idea of use the best curve you can sketch and try to evaluate A. Then there's uncertainty in the values of A and P, and that's related to the statistics of the situation. So I'll come back to this, but again, this is in parentheses, and it's beyond the scope of what you would do right now, although when you learn a little more mathematics, it's something you want to be able to do. But you need a good course in calculus before you can deal with this. So now question, is our data normally distributed? Okay, what's data? Well, our timings. We time, 30 to 100 cycles of the pendulum, and then ask ourselves, is that timing normally distributed, so that we can kind of use the bell-shaped curve to estimate the characteristics of our data. Now, you want to keep in mind that you can do this. You won't have become an expert at doing this, but you can at least apply the overview in a couple of basic ways. We know that 2/3 of your data should be within a standard deviation. We know how to calculate mean and standard deviation, and if you've forgotten that, review it. And it's likely that you've forgotten the steps for standard deviation. With a little review, it becomes very clear. Something you want to always know how to do. And come back to it 3 or 4 times over the next year, and you will. And maybe less than that. Maybe you already remember, maybe you know. Remember that the normal curve, of course, is a composite. We take a value of x, we calculate the power function, negative x squared over 2, to get a value that goes with the value of x. And then we feed that into the exponential function. Okay, and I suppose I shouldn't use exponential of x, I should use exponential of u, where u is your negative x squared over 2. Now you did this in 3 steps using Excel, so you have some idea of this chain of calculations and why this is a chain of functions, or what we call a composite function. If you feed negative x squared over 2 into the exponential function, you get e to the negative x squared over 2, where e is a very specific base for the exponential function. And that's a composite function, and that's what you graph to get the normal curve. You punch that into your graphing calculator and put the right range in and so forth, you're going to get that curve. But I advocate putting your graphing calculator away unless you're absolutely required to use it until you're at least a junior in college. Okay, and I'm serious about that. That's the way they do it at University of Virginia in their engineering program. So there's good reason to consider minimizing your use of a graphing calculator. You bypass understanding by using a calculator. Sometimes it's necessary, but you shouldn't be doing anything where it's really necessary until you're at least a junior in college. My opinion of UVA's engineering department last time I heard. Then I mentioned in our analysis things like standard deviation of the mean. That's important. That's part of understanding the mathematics, but that's a little more subtle. Take a good introductory statistics course, which will be completely accessible to you once you've completed a pre-calculus course. Even a good Algebra 2 course would prepare you for most introductory statistics courses, and you get into that idea. So it's not a deep idea, but I'm not going to get into it here. And then you look at uncertainties, and you see how we used the idea of a standard deviation to estimate our uncertainties. Having estimated the uncertainties in your data and the uncertainties in your results for the period of a pendulum at different lengths and with different ways of supporting, handheld versus well anchored, and you could maybe come up with some other, suspended from a balloon. See what that does to it. Okay, well, anyhow, you then, if you have a good handle on these uncertainties, can, with some fairly sophisticated mathematics that we won't touch here, if you really want to know about it, email me and I'll explain it. But we get the uncertainty in the values of our constants A and P that determine this function. And then maybe we compare with ideal models. Okay, I've given you an ideal model, and actually we don't even need to put that in parentheses. That's something you can actually do. Understanding where to get the ideal models using the V prime equals negative G over L times X, and X prime equals V, which you can model in Excel with very short time intervals, gives you something very close to the ideal model, and also allows you to numerically evaluate these constants. So there's all kinds of mathematics involved in this, and it's the mathematics that we spent Governor School developing.